Hey everybody, my name is Max, and I'm a web developer. And for the past maybe 2 years, I've been learning to make art with WebGL. And it's really been kind of like the most fun and rewarding experience that I've had programming lately, because when you're using WebGL, what you're really doing is you're programming your GPU. And so I want to talk to you today about how you can learn to program your GPU and how you can do it not alone. So when I say like not programming alone, what I'm talking about is stuff like this. So I'm sure that really frequently you go about solving some task with code, and one of the first steps, or just like a very common thing you do, is you start by requiring some code from maybe, elsewhere in your code base, written by your teammate or your previous self or someone on the internet who you've never met. And it's a really, it's a core part of what it means to write code in 2018, to write JavaScript. And it's maybe like so mundane that you might not think about the fact that if you run this code here in your browser, it doesn't work. Like, require is not defined. This is not a thing you can actually do in JavaScript necessarily natively. And the only reason why this stuff works and you're able to require code so easily and use it in the browser is because of all these tools like bundlers that are essentially implementations in like the user space of these module systems to kind of like port them to a browser environment that doesn't have them. There's like compiler engineers or browser engineers here, so I have to be careful because now I guess that like JavaScript is kind of gaining this ability natively, but still you kind of have to use Webpack and Browserify to easily use code from multiple places as if it was this big one seamless package. The way these things work is it looks into your JavaScript files, it looks for places that you're importing and requiring other code. It goes to those modules, sees what they require and import, and so on, and kind of builds up this big graph, both of code in your code base, code from node modules, whatever, and then kind of concatenates these files and bundles them all together and organizes it correctly into one file that your browser is happy to run and no longer really has like requirement statements in it anymore and is one big mess that's, but you still got to write your code as these nice individual modules and think about it in this way. So this kind of pattern has become this extremely ubiquitous, successful abstraction that we all rely on to ship code to browsers nowadays. And it's really kind of like resulted in this huge JavaScript renaissance where the low friction ease of sharing code and reusing code has led to a huge amount of collaboration between people who never meet each other or who do meet each other, and a large amount of fast spread of ideas in the JavaScript ecosystem. And it really is a big part of what has made writing JavaScript so powerful and fun and useful nowadays. So I told you that we were going to talk about programming your GPU. And one thing about a GPU is that you can't run JavaScript on it. So what your GPU is it's this thing in your computer. It's not just like fancy gaming computers, like smartphones. Basically all consumer devices have some sort of GPU nowadays. And it's a lot like your CPU in that it's like a processing unit that reads instructions and adds numbers together and does work, but has some core differences. One of which is that your CPU maybe has like 4 cores, and so it can be running like 4 different instruction sets at once. You've got like Slack and like your editor and Spotify or whatever going, and your GPU doesn't have like 4 cores, it has maybe like 2,000, like orders of magnitude more number of cores, and so it can just be like inherently running many more instructions all at once in parallel and can crunch through significantly more data all at once. But on the other hand, it's kind of got this core restriction is that it's a lot less flexible. And one of the specific ways that it's less flexible is that all of those cores essentially need to be doing the same instruction set at once. So whereas your CPU can be running like 4 different applications, all kind of doing their own instructions and processing different data, your GPU is really one set of instructions running in parallel on lots of different data. So it's kind of like, taping like 4,000 pens together. And so it's very powerful, can do things very quickly, but also has these constraints. And GPUs were designed this way because there's all of these tasks that really require this kind of work, and they're really common in kind of visual and interactive applications where you have thousands and thousands of pixels on your screen that all need to be updated with a color, and the work to do so, to do it 60 times per second, all on one core, would just be impossible, and that's where GPUs were designed to do. And WebGL is essentially APIs in browsers that let you write code that will run on the GPUs, and so you can have all these really cool, rich, interactive experiences that are interactive and 60 frames per second, even in your browser, and ship them to people, and it will be supported. So what are you doing when you're programming your GPU is essentially you're writing a shader. And a shader is the equivalent of a program, but what it is essentially a function that takes in some inputs and returns some outputs. And so, and it runs many times, and all of those executions are isolated from each other and don't know about each other and only think about themselves, but it's the same function running on all of them. So for example, the inputs might be the X and Y coordinate of the screen, and the output might be a color to display for that pixel. And so, you have every X and Y coordinate pair on your screen, and each one of them will independently decide on what color to render, and you'll receive an image. So I said earlier that these shaders can't be written in JavaScript because there's a few, the GPU cores can't really run JavaScript. There's no heap, it can't allocate memory, that kind of thing. So that's not gonna work. But there's this cool language with, in my opinion, a really bad name called GLSL. Hard acronym to say, but it's essentially a subset of C in that it's got a C-like syntax, so it looks kind of familiar, except there's no heap or really memory management. All you do is you have functions and loops and if statements and numbers, and that's pretty much it. So this is hello world in GLSL, and you might notice that there's no hello or world because there's no strings in GLSL, but you do have vectors, which are basically just arrays that have a set size and numbers. And so this is the hello world GLSL, which is here's this function main, no matter what happens, set the pixel color to red. It's red because it's the red, green, blue, and alpha values of the pixel. And this gets executed independently on every single pixel, and every single pixel decides, runs this code and says, yep, I'm red, and then the result is this big red square. The interesting thing comes when you start to use your inputs to do some math or make decisions on what the color should be. So for example, here, we're looking at the X and Y coordinate of the pixel that the shader is running on, and we're saying that if the X coordinate is larger than the Y coordinate, then the color red should be all the way red, and otherwise the color should be no red. And then when you return this color at the end, you'll either get, each pixel will independently decide to be red or black, and the emergent result is you get this triangle. And this is kind of a different way of thinking about what you're trying to render than a normal kind of Canvas graphics API, where you might say, draw me a triangle from point A to B to C. In a shader, you instead say each pixel decide whether or not you're in the triangle and render accordingly. And so it's, this different approach is interesting because it's not just, at first it seems like, oh, how would you get anything done? But it's actually, it makes certain things much easier and certain things harder. And so, but the way that you build up more complicated programs is you just kind of use more math and more if statements and more loops to decide this color. And so if you want to repeat something, you might use the modulus function on your inputs, and that would kind of make your inputs wrap, and that would make your image wrap. Or you might use sine waves and min and max and kind of just standard library seeming math functions, but you can go a long way with them. So this is a shader written by somebody who's very good at writing shaders. I think they go by Big Wings on shadertoy, which is a website where people share shaders. And it's really beautiful. This is just math functions deciding what color each pixel should be, but the result is this image of cars traveling on a road at night through a rainy windshield in an out of focus lens and everything. And it's a really beautiful image, and it runs in your browser and it's interactive. And so you might wonder, okay, how can I make things like this? This is cool. And if you go and you look at the code for it, you might be kind of scared and shocked because it's like 400 lines of all of this math stuff, and there's not really, it's just a different kind of program structure they might be used to. It's all one file, there's no strings, and so I would say that, like, first of all, one cool thing about shaders is because they're just passing numbers around and deciding pixel colors, you can really just mess with this stuff, and like the ways that you break it are going to be interesting. Like, you know, in maybe a normal program, you break it and it just makes a wrong output. In this, you change some number somewhere to see what happens, and the result will change. And I don't know, it's like GLSL has the best bugs because everything is pretty. The other thing that I want to point out about this 400-line file is that actually, upon closer inspection, you'll find that very large chunks of it are these like helper functions, which have nothing to do specifically with this application whatsoever. Like, they are methods that anyone writing a shader might need to use, and this person didn't write custom in order to make this shader. They probably, you know, there's even links to places where they kind of picked them up from other people's shaders and pasted them in. And this is just kind of a really common thing in shaders, is that you'll have this big preamble of functions defined at the top that you found in different places because they were useful to you and you just stuck them into your file. And so maybe if this was written kind of in a way that more logically separated the application-specific code to the like general purpose utility code, it would be a lot less intimidating to read and to edit and to learn from. So I'm going to work through a little example here. So there's this really fantastic algorithm called Perlin Noise. And it's basically like randomness, but it's smooth randomness. And so things that it gets used for all the time are oftentimes like simulating kind of natural shapes. And so if you want to make clouds or fire or water or rocks, oftentimes really what you're doing is you're combining Perlin Noise with like more Perlin Noise with more Perlin Noise. And it's like an awesome building block. It's really indispensable in making building shaders. And it's actually such a good algorithm that it won an Oscar. Not a lot of algorithms can say that. And so in order to like use Perlin Noise, all you really need to understand is that it's this space. Maybe it's like a one-dimensional or two-dimensional or three-dimensional space. In this case, it's two-dimensional. And you give it kind of like, you index into it, meaning like you call a function with some arguments of like the x-coordinate and the y-coordinate, and it tells you back a value. It's this very kind of simple function with inputs and outputs. And so that's logically all you need to know all you need to know to use it. But if you go to try to maybe like build a shader that uses it, you might find like a paper that describes implementation of this. And it might have some really cool but also scary diagrams and like weird MATLAB pseudocode. And like none of this stuff might be interesting to you, but it's not what you really need to use it. Or maybe you'll find like some blog post where somebody implemented it in like GLSL in 2012, and you can kind of like pick this up off the street and dust it off and paste it into your code and paste it into the top of your file. You'll see that it itself has other functions it relies on, so you have to make sure to bring those to, make sure they don't like have the same name as any of the functions you're already using. And when you're done using it, you need to make sure that you delete it, or else your file will just get larger and larger, which most GLSL files do. And so there's even like gists kind of that people pass around, and like it's really common. You'll find some like useful piece of code somewhere that will itself have references to where they found it from and dusted it off and shared it around, and like these links all inevitably are dead if you follow them back long enough. And it's just this like weird world of not really writing code the way that you might be used to in the nice world of JavaScript. And so wouldn't it be nice if you could just npm install this and it would live like in your node modules, and you'd have this dependency that you could keep track of and update when it got, and delete when you didn't need it anymore and share easily. And luckily, there's this cool tool called GLSL of Phi, which much like browser Phi for JavaScript, implements like a module bundler for GLSL, the language that also does not have innately a module system. And so GLSL, similarly, will read your GLSL file, we'll look for other GLSL files that you import, we'll go find those in your file system or in node modules or whatever, pull them in and bundle it all together into one single GLSL file that will run and you basically have like a module system implemented by this tool. So to kind of look through an example of what that looks like, this is an example of using Perlin Noise, where we've got this kind of like import statement. It's really just like a comment, but it's a special comment that the tool knows to look for at the top. And then we use it as if it exists and do our thing, and it only takes 3 lines. We can start playing with Perlin Noise. And then the reason that this works is because this code here, after it's been run through GLSL of Phi, gets expanded to this, which you can see here like includes both the like Perlin Noise implementation, the dependencies of the Perlin Noise implementation that we didn't even think about, and then at the very bottom right, basically our original code, but they kind of changed the name of the function, mangled it so that it didn't conflict with anything else, added some numbers to it. But, and this can run in a browser, and this will work. So on top of that, not only did we get a really nice ease of installation and use, we also got all these awesome benefits for free where we're installing this in NPM, and so we have like versioning, and maybe even it's semantic versioning if people are being nice to us. And there might be like a page to a source repository where there's a README and some examples, and people have opened issues and closed pull requests, and there might be a license and like continuous integration, and all of these things that maybe are mundane in the JavaScript world make a huge difference when you didn't have them originally, and can really like help build a community around an ecosystem. So I want to give you now like a little tasting menu of some of the cool things you can import in the like GLSL of Phi module world that maybe would inspire you to go try them out and build something cool. So it's Pride Month. You can install HSL to RGB, which essentially is a it's like HSL is a color space like RGB, but it's the H and S and L are hue, saturation, and lightness instead of R, G, and B. So you can, make like a gradient through not just, you can basically sweep through the hue space and barf rainbows all over the place and have fun that way. This one's really fun to animate. There's this one, GLSL Rotate, which essentially implements like rotating vectors, which is a surprisingly hard problem. Not to like think about, like everybody understands, like, okay, I have this vector and I want to rotate it to point in a different direction, but the math to do so is unneededly confusing. There's this word called quaternions, but basically, if you use this library, you don't have to think about it. You can just rotate and make the thing you want to make and not worry about the details there. There's a dithering algorithm you can install to make cool, like retro 1-bit art. And one of my personal favorites is GLSL Raytrace, which is an implementation of a ray tracer that runs in a shader, which basically allows you to define like a 3D shape as a math function and then have it visualized for you. And it's really fun, it's really weird. And you can do it in just a few lines of code. And so basically, like one of my points here is that each of these modules is small and understandable and has this API surface that you can look at an example of and understand quickly, and it can be a really great ladder rung towards learning the greater ecosystem when everything is broken out into these small things that you can grok and use and dispose of when you're done. It doesn't, you're not responsible for like maintaining it or anything. And this, for me, was one of the breakthrough moments for me to learn things was having things logically separate into modules that I can read and understand and peruse to see what is possible. So what I want to leave you with here is that the ability to like easily leverage libraries is not just a convenience for lazy programmers to save time, but like the code that you import and leverage really is a fantastic teacher and guide as to what is possible and how to communicate with other developers. And it's a big deal, and it's a privilege to be able to be part of a community where it is so emphasized to be able to make your code shareable and reusable and useful to other people because there's benefits besides saving each other time. Like it really is a form of teaching and collaboration. So thanks for listening. And if you want to learn GLSL, I can't recommend enough this website called The Book of Shaders. It's not a book, it's a website. It has really fantastic like pictures and metaphors and interactive examples. It's really good. And yeah, thanks for listening.
I thought you were going to announce GLSL PM. That's what I thought this talk was going to culminate in. How big is this community?
That's a good question because the JavaScript community has a lot of money in it lately, by which I mean lots of the tools you use nowadays are sponsored by big, huge companies and used to make websites that generate lots of money. And WebGL is kind of this weird little island of non-commercialism. And so a lot of people who do it are not being paid for it, and it's this really small ecosystem, and they're really nice people and put a lot of time into teaching. And so it's kind of one of the things that makes it fun for me is that a lot of the applications are for people's gratification and fun. There are people doing mapping and stuff with it, but a lot of it's a very small number of people who build these tools.
That's cool, because even within the JavaScript community, there's a lot of people who push back on, programming with modules or using NPM, and so it's interesting to see a community adopting all that stuff that JavaScript has, but it makes sense that when you are small and you don't have corporate funding. I was talking to Pia, who's a creator of Open Collective, about this the other day. I was like, I make open source software, but not developer tools. Google's not gonna fund my make8bitart.com project, you know what I mean? So it's always interesting when I talk to other people who are in that sort of boat, how do we get support around those kind of things? Have you seen developers who are doing WebGL and making this kind of stuff looking for forms of funding, like Patreon and stuff like that, or is it mostly people who do this on the side?
It's a good question. I know that some of them are just anarchists who live in Hawaii. And I think they have a consultancy or something, but I know that a lot of it really is just people who do it because they want to make art and want the tools to be good and maybe have a side job, but I'm not sure about any Patreons.
How do we get the Hello World pixel to be blue instead of red? Who do I talk to about that?
Well, I mean, I guess that, to be honest, I oftentimes see when people do tutorials, they oftentimes use cyan or cyan. I don't know how to say that word.
Cyan. Yeah,
cyan.
Whatever.
Yeah.
GIF.
So, is that blue enough for you?
That I'm good with cyan, even though that's very much like a print color kind of thing. So it's kind of, I like that. It's ironic almost, WebGL print color. Another important question is, I wrote an algorithm once. How do I get it to win an Oscar?
So it was kind of I think the title on the Oscar was something overall contribution to the movie industry. So if you can get your algorithm used in the next 5 Toy Story movies, I think you've got a shot.
Jort sort is implemented in RxJS, so I think I can. I think I can do that. Awesome. Do you? What do you think? Those in here who are interested in GLSL. We need to change the name of that. Mm-hmm. Yeah, that's the first thing. Where should people go besides reading the Shaders book? Is there a specific forum or mailing list or GitHub repo that people can go and read conversations and get a feel for what the community is like, since it is so small?
Yeah, definitely. I think that 2 good places are, one is shadertoy, which kind of has the community is basically people posting cool stuff and other people saying wow, this is really cool, nice job. But it can be a great place to get inspired and see what's possible. Another one is that weirdly, there's this tool called Regl, R-E-G-L, that has a really active Gitter chat room, and people are asking questions there all the time, and they're really helpful.
Cool, awesome. Thank you so much. Round of applause for Max and GLSL.